I'd like to talk about chaotic strings in the context of the AdS correspondence. Especially, I'd like to talk about what is called chaotic strings. And this talk is based on the collaboration with Lyapunov, Daisuke Kawai, Hideki Ono, and Kenta Yosha, both are in Kyoto University, and Yosha Kenta also in Tsukuba. And the details are written in these two papers, so if you're interested, please read these papers. Okay. First, I'd like to talk about what is our motivation to study chaos. In order to talk about that, I'd like to briefly touch the famous historical fact, that is, the findings of the integrability behind the AdS correspondence had big impact on the development in the study of type 2 string and 4-dimensional both superimage correspondence. For example, one rotation operator in the gate side can be written in the same form of Heisenberg's Pinch Hamiltonian. So this operator can be solved exactly. And moreover, co-canonical potential is also exactly solved because minimal surface can be solved exactly based on the integrability technique. So we can say that the development of study with integrability is a key ingredient for the understanding of the dynamical aspect, like spectrums and potentials of the AdS correspondence. But there are important points. That is, there are no integral systems in the AdS correspondence. For example, these 10 backgrounds are known to be non-integral backgrounds. So, important question is, what measure is useful for the study of non-integral systems like this background? This is our basic question. And it is known that classical strings on non-integral systems usually have chaotic motions. For example, in the list of last slides, strings on AdS 5 plus T11, AdS solidons, and AdS black hole is known to exhibit chaotic motion. So we study the way to uncover the dynamical aspect of non-integral systems with quantities specific to chaos, like promotional entropy and corrector dimensions. And today, I'd like to talk about promotional entropy and related laws mainly. And these days, there are a lot of related laws on chaos in the study of string theory. For example, Maldacena Senka and Stanford claims the existence of upper limit on the Lyapunov indices. Later, I introduced Lyapunov indices, but this now I'd like to say that this is very important quantity for the study of chaos. And aspirant Berenstein-Galusha says that claims that the growth rate of intermediate entropy is limited by Lyapunov indices. And Prosinski discusses the relationship between the time evolution black hole and chaos. So chaos is becoming hot topics in the study of chaos. Okay, and you might think that chaos might be important, but what is chaos? And next, I'd like to show you the characteristics. Unfortunately, the definition of chaos is not fixed yet, but most people think that the following three features is necessary for the chaotic system. First, the system should have random trajectories, which is not driven by stochastic noise like Brownian motion. So this random trajectory is driven by deterministic force. And the more important point is high sensitivity to initial values. The meaning is that if two trajectories in the system have tiny difference in initial condition, the difference grows exponentially. So we can't predict real-time behavior. This is the reason why phasor forecast is difficult. And this point varies from 2%, but usually boundedness of trajectory into finite range is said to be necessary point. From these three features, important point is derived. That is, system is deterministic, but information is produced in the time evolution. The meaning is as follows. First, trajectory is governed by UM without the stochastic noise as pointed out in feature 1. So if we set sufficient initial condition, the trajectory is uniquely determined. However, as I said in picture 2, the time difference in initial condition grows exponentially. So this time difference makes significant difference in the time lifetime. In informatics world, this is said that information is produced, and this factor is reflected in positive Hormone-Stein entropy. This is the physical meaning of Hormone-Stein entropy. Okay, and next I'd like to show you a well-known chaotic system, namely Lorentz model, between this differential equation and trajectory draws this kind of strange attractor. And now I show you two trajectories. And please be careful that the initial difference in initial condition only 10 to 6 minus power. But yeah, now we can see only green lines. But at the time of 20, yeah, this red line appears. I'd like to stress that this difference is only order 1. So at the time of 20, this 10 to minus 6 powers difference grows order 1. This is the characteristic of case. Okay. And next, I'd like to show you how to measure chaos quantitatively. Namely, I'd like to introduce these three important quantities. And now I introduce them by seeing the case of Lyapunov system. Okay. And this is the Hamiltonian of Lyapunov system, and it is known that Hamilton system which exhibits case. And first term is well-known harmonic oscillators term, and here nonlinear interaction is introduced. I don't have enough time to subdivide this, but I will say that this Hamiltonian can be derived from this three-body periodic lattice in this form. And this is first studied in the context of planet motion. And now I'd like to show you how to draw boundary section. First, we consider a section as not crossing with trajectories or in phase diagram governed by UN. Then we take a point on S naught, say X naught, and consider time evolution of X naught. Then the center point on X naught reflects the integrative structure of the system. For example, the system is integrable and trajectory is periodic. Then the picture drawn on S naught is periodically arranged orbit, or in the case of closed periodic orbits, closed orbit is drawn. However, if system is non-integrable and features chaotic motion, then on S naught, randomly scattered points are drawn. So we can see whether the system is chaotic or not by low-dimensional picture. And this is the numerical result of Lyapunov system at the energy is equal to 0.833. We can see a lot of periodical arrangement pattern in this low-dimensional picture. But by doubling energy to 0.1667, completely scattered point occupies whole phase space. So we can say that the Lyapunov system is chaotic. Okay. And more quantitative one is Lyapunov spectra. As I said before, in general, the difference of trajectories grows exponentially. For example, initial difference is delta x0, then difference at time t grows in this form. So lambda in the exponential is Lyapunov indices. So lambda is positive, we can say that the system is sensitive to initial values. So this means the system is chaotic. And please note that, I'd like to say that we can get any Lyapunov spectra for any dimensional system, because we can measure sensitivity to initial values for each direction. And important equation for Lyapunov spectra is Pageant equation. this equation says that column-Schneer entropy small h is given by the summation of positive Lyapunov spectra. So Lyapunov spectra calculation reveals the existence of chaos, and we can get the information about the growth rate for the information production. So this is very important quantity for the study of chaos. Oh, sorry. The figure is rotated, but I will introduce. And this is the numerical result of Lyapunov spectra in the system with Shimada-Nagashima algorithm. Sorry, this direction is time, and this is Lyapunov spectra. And the circle is outside the region. Here, please, please focus on this region. In this Shimada-Nagashima algorithm, we can read spectrum from later time evolution, and red line converts to positive values. So we can say the maximum index is positive, and the system has chaotic motion. So we can conclude, a system is chaotic system. Okay. This okay. Now I finish the brief introduction of chaos, and I'd like to show our work on the chaotic strings in a near-zero limit of AdS factors T1. First, I'd like to briefly show the strings theory on AdS factors T1. The metric of AdS factors T1 is written in this form. Here, large R is AdS radius, and the metric is consists of AdS part and T1 part. And in this metric, we consider Bragg action under the Virasov constraint. And it is known that type 2B superstring on this metric is there to 4-dimensional n equal 1 superconfirmative cell. And from the work by Basu and Pangzayas, it is known that there exist chaotic strings on AdS fibers T11. And our question is that the following. Chaotic strings persist in a near-Penrose limit of AdS fibers T11. I think this is a very important question, because if chaotic string exists, it means there near PPS operator in the Derivatives theory, namely 4-dimensional n-1 superconfirmative theory. And we revealed the existence of chaotic strings in near Penrose limit. So in our conclusion, there are two strings on this metric. There are unknown, but chaotic operator exists. Yeah. Okay. And next I'd like to show our prescription for the limit. First, we defined coordinate by this coordinate transformation, and we scaled with AdS radius. And we expanded metric by the order R inverse squared. Of course, first term is PPA background, and this is a near Penrose collection term. And here is the exact form of our metric, but this is not important here, so I crushed it. And we take right conjugation Hamiltonian and expand it by the order R inverse squared. Then we take an ansatz in this form. And the physical meaning of this ansatz is first, we pinned strings on a point in the AdS direction. So this strings moves on the T1 part. And lastly, we got this Hamiltonian. And this interaction Hamiltonian have influenced as a source of chaotic strings. So this is important. And this is the boundary section at the energy is equal to 10. And by chaotic term, periodic orbit and chaotic lines are mixed. But by restricting momentum in the direction R2 is smaller than 5.2, we can see chaotic pattern is appearing in the phase space. So we can say that chaotic strings exist in this limit. And this is our study for the reason for the appearance of chaotic motion. And this is the energy control of AdS cycles T1, especially in the direction of separatrix is a point to different kind of orbit is divided. So here, small orbit and elliptic one and larger orbit are separated. This separatrix structure sometimes collapsed from the higher order interaction, and such a collapsed separatrix sometimes serves as a source of chaotic strings. And in this case, this separatrix is collapsed, so chaotic strings appears. This is a reason for the chaos chaos in this system. Okay, let me summarize my talk. First, we proved the existence of chaotic strings in New York Aero's limit of AdS 5 plus T11. And in this case, separatrix serves as a source of chaos. And as a future direction, we'd like to pursue the understanding of chaos in the database theory with content specific to chaos, like chromosomal entropy are introduced, and fractal dimensions. And lastly, I'd like to say that study of AdS by chaos might be one possible path for the understanding of non-autonomous system. Okay, thank you for your attention.
Any questions?
So in this case, they will not have chaotic string for AdS 5 plus S5.
Yeah. Yes.
Because it's integrable.
Yeah. We today I didn't show you, but we tried AdS 5 plus S5 case, and there is no chaotic motion in that system.
So it's because it's integrable.
Yeah,
system.
very so.
Anything else?
It's having H coming, so can you study some other something like AdS 3, AdS 3, or some other?
Yeah, of course. Possible.
So it's not essential to have like 10-dimensional space time.
Yeah. Yeah.
Have you found any pattern in the Lyapunov exponentials? Have you tried?
Yeah. We tried Lyapunov indices calculation for this system, but maybe I don't have definite result. Maybe because this graphic term has bad impact on the Lyapunov Shimada algorithm